We consider this planet more of an Earth cousin than an Earth twin. Our galaxy is probably littered with cousins of Kepler 186f.
The Interplanetary Podcast. The exploration of space for the benefit of all mankind. Your hosts here in London, Matthew Russell and Jamie Franklin.
Oh yeah, baby, Eliza Quintana.
I like to refer to her as EQ.
EQ. Yeah,
I mean, come on. On this day, 50 years ago, 1970, Apollo program, Matt.
Yep.
Ill-fated Apollo 13 returns to Earth safely.
What is often regarded as the most dramatic of all space missions.
Pretty dramatic.
In 2014, NASA made a public announcement that Kepler Space Telescope and Eliza Quintana et al. Had discovered the first Earth-sized planet, Kepler 186f, in the habitable zone of another star. 582 light years away.
Incredible stuff. Now, Matt, we've got a sad moment in the podcast. Rest in peace, John Conway, inventor of Game of Life.
Yeah, hugely influential maths guy. Loads and loads and loads of stuff. Very influenced Brian Eno. Brian Eno loved that Game of Life thing.
God, he did.
Yeah, I've got a great interview today that's going to have to be split up because it was 2.5 hours of talking to Kelvin Long about interstellar travel.
Well, let's be honest, Matt, that's a 2.5 hour conversation if ever we heard one.
It is. So we've got interstellar travel. I will do most of that conversation in today's podcast. However, I shall be moving the second chunk, which is about conscious stars. How about that one?
Ooh.
Conscious stars.
You had me at conscious, to be honest.
Conscious stars. Any Rudy Rucker fan out there will know what I'm talking about. That should be interesting. So I'm going to move that over to Patreon.
There we go.
So you can listen to that there during the week when you're bored.
Boom.
Jamie, what was the big news this week?
Wow. Should we talk about Flat Earth?
Let's talk about Flat Earth.
I mean, Matt, how many views have you now got on the internet?
I don't know. It's considerably more than we get on the podcast anyway.
Definitely more. Do you want to give us a bit of context for anyone who didn't see our Instagram post?
Yeah, so there's a channel, a UK channel, although I think it's quite big in Australia as well, called Ladbible.
Okay,
Ladbible, and it's pretty big, isn't it? Ladbible, and they run a thing called Agree to Disagree, and it's me, who they've called a scientist, which is, let's face it, a little bit. That's probably the most inaccurate part of the whole thing.
It's pushing it,
and it is definitely pushing it. I like to think of myself as a science communicator rather than a scientist, and yes, it's scientist versus flat earther, and yeah, it came out this week. And it was quite scary, Jamie. I bet it was.
I was very proud of you.
Reputation.
You held your own, and you didn't get ruffled by the nasty flat earther. You did very well, mate. You did very well. He's not nasty. He's just got an opinion that's wrong. That's all.
Yeah, and remember, he's probably a nice guy, and
sure he is.
It's his opinion that you should hate, and not him.
Exactly.
I'm very proud of myself that I stuck to that adage. It's quite hard sometimes.
Of course. So go and check it out.
Now, I just wanted to address just one thing where obviously the edit makes it look as though I was sitting there going, oh, okay. It got me thinking. He was saying, oh my God, the Chinese space program is so ridiculously obviously fake. And I was thinking, what's he talking about? Because as we know, the Chinese space program, particularly right now, is pretty kick-ass. Although they've had a couple of rocket failures recently, which is a bit worrying.
Matt, he referred to bubbles coming out of helmets, that all of their footage was underwater. What's going on?
He can only be referring to one event, And that because China became the third country to independently carry out an EVA, an extravehicular activity in a spacesuit. They've only done it once, and that was on the 27th of September, 2008, as you know, on the Shenzhou 7 mission. And that was astronaut Shai Xingang, and he was wearing the Chinese Phaeton spacesuit, and astronaut Liu Boming wearing the Russian Orlan spacesuit, helping him out. So they're the only two Chinese people that have ever done a spacewalk, i.e. the only people that would be wearing a space helmet that you could possibly see bubbles. Now, I've watched the footage, and I can't see what on earth he's talking about.
No.
And the only thing I can think of is that someone's found footage of them practicing in the pool, which obviously you do, practice your EVA in a swimming pool, because it's the only way you can practice.
Exactly. We've been to one.
Yeah, we have been to the one in where was it again? It was in Cologne.
It was in Cologne.
The largest European testing pool.
Yeah.
And yeah, obviously you might see bubbles then. Maybe they've seen footage that has been poorly translated, i.e. from the Chinese to the English, and it's been translated in such a way that it looks like it says that they're doing a spacewalk rather than practicing a spacewalk.
Right.
So maybe that's, I just don't know, but it just is clearly crazy. And I just thought that was interesting. I thought it was just interesting that China have only done one EVA themselves, and that was, Shenzhou
Absolutely.
7.
Well, big shout out to the Chinese space crew. We love ya.
Well, I want to do another big shout out to previous guest and patron Tupper.
Yes.
From old Annapolis.
We love Tupper. How you getting on, buddy?
He has sent in a little update about Osiris-REx, little spacecraft out in space, and has been practicing landing or doing its little scrape of Bennu.
One step closer, eh?
A 4-hour checkpoint rehearsal.
Oh.
It comes out of orbit, then does a checkpoint burn, which basically puts the spacecraft in a position where it checks its own trajectory.
Yeah.
And works out how it's going to get down to the asteroid and do this scrape. Because it turns out that this maneuver is so much harder than they thought it was going to be, because it's this asteroid, Bennu, is much more rocky and boulderous than they thought. So
it is.
It's going to be very, very hard. So the spacecraft has to rely on its own cameras and its own skill at avoiding boulders. So they've been practicing this maneuver of going down and doing all this and looking at the thing and testing out all the equipment.
Yeah.
They even managed to deploy the sampling arm and things like that with the touch and go sample acquisition mechanism.
TAG-SAM.
The TAG-SAM.
Come on.
That all went very, very well, apparently. Exceptional, because the whole team, of course, working from home.
That's right.
You know, they're mostly working from home, and some of them are going in when they have to do critical things like this, including our friend Tupper, who is chief engineer at Goddard. His friend, Rich Burns, which I have to say is one of the best names for a project manager at a spaceflight centre, is Rich Burns. Fuel Rich Burns. I mean, it's just it's amazing, isn't it? Yeah, it's awesome. This is what he said. This rehearsal let us verify flight system performance during the descent, particularly the autonomous update and execution of the checkpoint burn. Executing this monumental milestone during this time of national crisis is a testament to the professionalism and focus of our team. It speaks volumes about their can-do attitude and hopefully will serve as a bit of a good news in these challenging times.
Beautiful. Rich Burns there. Osiris-REx, product manager.
I hope I haven't offended Tupper and his friend Rich, but absolutely legends.
Pair of legends.
Osiris-REx, I think, is one of the most underappreciated spacecraft there ever was. It's always having its little... It's always being outshone on a day there where it's done something special by another something special, like the Chang'e 4 or something like that. But yeah, what a great mission. So I can't wait. August the 25th, it's going down to do the actual drop down, where it drops down, goes near the surface, fires a charge of pressurized nitrogen that disturbs the surface, and then scrapes up what it's dislodged, and then brings it back to Earth on September the 24th, 2023.
Matt, if you were a betting man, what do you think that material is going to be comprised of?
Rock and dust.
Yeah? No platinum in there, or anything like that?
There's bound to be some precious metals and things.
Matt, we were talking about Rich Burns. Do you remember when we worked together and our accountant was actually called Bernadette?
Yeah, Bernadette Cook the books.
Shout out to Bernadette. Oh dear, true story. Oh, what else have we got this week, Matt?
Well, I think one of the most significant, or potentially significant, news stories for a while. Yes,
yes.
It might be a very. I mean, the indications are here. We're sort of moving towards an explanation about why stuff exists.
Ooh, it's a big question.
Why are planets and stars and things like that made of matter, and not some made of matter, some made of antimatter, etc., etc.? At some point, more matter was made than antimatter immediately after the Big Bang, and if the whole universe was somehow symmetrical, that wouldn't have happened. Equal amounts of antimatter and matter would have been made in the Big Bang, and it would have all annihilated each other, and there'd be nothing left. Right, so just energy.
Yeah, of course.
But luckily, something happened that meant there's way more matter than antimatter. This new paper called "Constraint on the Matter-Antimatter Symmetry Violating Phase in Neutrino Oscillations."
If you are not reading this in lockdown, I mean, come on, you've got to ask yourself, what are you doing?
What are you doing? Well, luckily, Nature broke this down into several articles, including a brilliant one in Quantum Magazine, I have to say, what this paper actually means. But I thought I would take the story even further back than they do, because they kind of assume that you know quite a bit of stuff, right? Are the laws of physics symmetrical? As in, when you look in a mirror, for example, do you see the same thing but happening in reverse, for example, or being reflected back at you? And it would be really odd, wouldn't it, if you looked in a mirror and some things were reflected correctly and other things were reflected differently? So your kind of sense is that the rules of physics are symmetrical.
Yes.
And it almost seems odd that they're not. But there was a big dent to this in the 1950s when parity was violated. So they were testing beta decay of cobalt-60 nuclei.
Oh, yeah.
Cobalt-60 is made in sort of nuclear reactions from nickel, I think, or iron, and then goes back to nickel. But beta decay, i.e. a neutron transforming into a proton by the emission of an electron accompanied by an anti-neutrino, and you'll see how important neutrinos are in a minute.
I'm with you so far.
An experiment was carried out by Shang-Shul Wu, and he demonstrated conclusively that weak interactions violate parity symmetry. So in other words, some reactions do not occur as often as their mirror image reactions, if we take our analogy a little bit further. So overall, the symmetry of this quantum mechanical system can be restored if you add another form of symmetry. So that you can say, this one's slightly out, but this one's slightly out in a different way, and you combine the two, and you get back your symmetry. So shortly after P violation, this parity violation, they said, well, maybe there's a charge symmetry that's going out at the same time. So you get CP symmetry. So you put the two together and the symmetry then restores this symmetry. You've got the two, one slightly out the other way. You get your symmetry back, right?
Right.
And that was proposed in 1957 by Lev Landau. And so that's the charge conjugation symmetry between particles and antiparticles and you put that with your parity, and you get your symmetry back. However, CP symmetry, although it was proposed as a way of restoring symmetry after parity violation, unfortunately, in 1964, James Cronin and Val Fitch won the Nobel Prize, later obviously in 1980, but in 1964 they discovered that there was also CP violation, that kaons,
say what?
neutral kaons, yes, the way that they decayed actually violated CP symmetry. So, that totally shocked the entire physics world, and everyone was going, oh my God. Now, you can do the same trick again, it would seem, by adding a time symmetry into this.
Right.
So you add a third term to make it CPT, and that's now sort of a massive fundamental of quantum field theory. So between this charge, parity, and time, you get your symmetry back, even though each of those individually are being their symmetry isn't quite right. You get it back. Now, in some ways, you think, why do we perceive time as going forward? Well, CP violation actually is a kind of really weak arrow of time, that certain reactions aren't reversible because they're different when you time reverse them. So you kind of have to be going forward in time. But it's such a weak arrow. It's not the sort of full story. Entropy is always considered the sort of big, strong arrow of time. But no one really has a proper explanation for it. So,
arrow of time, sinking to the Nile.
Now, there was a guy. So, why are we even talking about this? And what the hell has this got?
I wish I knew.
Matter and antimatter, Jamie. Well, and honestly, it's one of the most beautiful experiments, and one of the most. When you look at it, you go, "This truly is a massive testament to human ingenuity."
Really is.
It's just so genius. So there was a guy called Andrei Sakharov, who was actually, when you read about him, he's a Nobel Prize-winning peace activist, Russian dissident legend.
Wow.
In 1967, he pointed out that there should be certain conditions at the right at the Big Bang that could produce more matter than antimatter. In other words, produce them at different rates. And he set about putting the list of conditions that would need to be met for that to happen. And one of the sort of big pillars of that theory is that there should be this CP violation. Now, we know that CP violation happens in quarks like kaons, but that's way too small to support that amount of change isn't enough to explain all the matter and antimatter disparity. So it's not enough.
Right.
So CP violation has just not been observed in non-quark elementary particles with enough certainty until maybe now.
It's what I've been saying for years.
Yeah, so they're looking for it not to be happening in the quark region, but more in the lepton sector.
Oh, finally.
And then if you get it in the lepton sector, you get this thing called leptogenesis, which does give you this enough of an effect, probably, to give you more matter than antimatter. So here's the really cool thing. So experiments since 1990 have shown that neutrinos, these amazing, almost massless particles that travel insanely fast and just don't interact with anything. So they're incredibly hard to spot, even though that you're just surrounded by them right now. Like your cup of coffee is filled with hundreds and hundreds of thousands of these things, if not hundreds of millions of them whizzing around, but you just never feel them. You never see them. They don't interact because they're almost massless. In fact, they thought they were massless, but their mass actually has sort of 3 different varieties, and it's not even connected to the to these flavors, and the mass actually can take on different values, and it seems to their masses are like a sort of quantum state. But anyway, this is more about the kind of flavor that these neutrinos have, their kind of leptonic flavor, which that actually flips between electron flavor, muon flavor, and tau flavor.
What's your favourite flavour?
I think tau flavor is my favorite.
Yeah, me too, definitely.
Yeah. And they sort of flip it in between all those different states whilst in flight. Now, it gets extra complicated because neutrinos are moving so
thank
fast.
God, because right up till now, I mean, I know exactly what's going on.
While in flight, Jamie, you kind of neutrino, because it's almost going at the speed of light, its frame of reference, time-wise, is completely different to ours. So we think it's taken a fraction of a second to go from one place to another. It thinks it's taken even shorter.
Oh.
Yeah, so it's like everything is super slowed down in the neutrinos frame of reference. But anyway, as they're flying around, they're switching between these different flavors of electron, muon, and tau, and that's both neutrinos and antineutrinos. So you get some antineutrinos being electron antineutrinos, and then suddenly they flip to muon antineutrinos, and so on, right? Now, there is an experiment because there's been some thought that maybe the antineutrinos and the neutrinos behave slightly differently, and that they switch between these different flavors in different ways and different amounts of time. And this would be the first case of CP violation in a kind of in the lepton sector. And which could then go on to explain this disparity between matter and antimatter, right? So there's this absolutely amazing experiment called the Tokai to Kamioka, the T2K experiment. And basically what happens there is a muon neutrino beam maker at a place near Tokai, which is on the east coast of Japan, where they make really good Strat copies.
Yeah.
There's also along with a guitar factory, there's also J Park facility. Now this J Park facility creates this beam of muon neutrinos and blasts it 295 kilometers through the Earth to Kamioka Observatory. Now, beneath Kamioka Observatory is the Super Kamioka Andi Neutrino Observatory.
Ooh.
And that is 3,000 feet below Mount Ikino, near the city of Haida.
Wow.
And yes, it's 295 kilometers away. And to see this detector, it is one of the most beautiful objects on Earth. But I'll talk about it a little bit later on because the way that it detects neutrinos is absolutely amazing. Now,
can we get a photo?
Oh yes, the photo will be definitely in the notes. It's one of the most incredible buildings there are. It's like a lake. Well, I'll explain it a little bit later on, but I wanted to just get onto the fact that at J Park, at the Tokai facility, you have the beam gets measured about 280 meters away from where they're being produced, and the neutrino flux, i.e., whether they're in these various different flavors, it gets tasted. It gets tasted by this detector, and it's like, they're this flavor, right? But then they're obviously detected again over at the Super Kamiokande Neutrino Observatory, and their flavors are then tested again. Little tongues all out there tasting the neutrinos as they go through. And of course, if you look at the difference between the two, you can start working out what the probability of these things change, flip-flopping from one to the other, and what's been happening. So the big question is, do neutrinos and antineutrinos change their flavor at different rates? Right, that's the big question. And this paper has used a long baseline neutrino and antineutrino observation. So in other words, they've been observing them for a very long time at this T2K experiment. And yes, it indicates that there is CP violation in these leptons, these leptonic flavors of neutrinos.
Wow.
And this is the first time, I mean, it's been observed before, but it could have been just a statistical bump. Now, this is where it has got up to 3 sigma certainty. So this is why this paper is being published. 3 sigma certainty means that there's only a 0.3% chance that this could just be a statistical bump in the data, right? So that's still a little bit dangerous. You can't call it a discovery. But what it does do, it makes it the first official evidence of a imbalance between neutrinos and antineutrinos, which, as far as I can tell, is absolutely massive.
Yeah, sure.
So, yeah. Now, the Americans have got another experiment called NOVA, which is very similar to this, and that's also getting very close to this 3 sigma certainty level. And even if you added those results up, you still wouldn't get to discovery status. So discovery status, which gets you the Nobel Prize, that is basically 5 sigma. And 5 sigma is 0.00006% chance that there's a fluke in the data set. In other words, just so extremely unlikely you can rule it out. It's called a discovery. And they're currently building the next generation of equipment to do precisely that, to get this data set up to that level. And that's called Dune and T2HK. But the amazing thing about this is that this neutrino-antineutrino imbalance has actually happened much faster than scientists thought it would, which means that actually they actually are as different as possible, they're as different as much as possible as they could possibly be within the standard model. So actually, that's for once the scientists have had a bit of a kind of easy break there. But unfortunately, Jamie, this is only half the story. All this has done is hint at this CP violation, but it doesn't necessarily mean that this is the story that leads to antimatter and matter being imbalanced at the start of the universe. So that all hinges on whether neutrinos are Majorana or Dirac particles.
What? Okay.
We're almost there. All the observed neutrinos that you see are left-handed, i.e. their spins are going in the opposite direction to anti-parallel to their momenta. Mm-hmm. And antineutrinos are right-handed. What's really odd is you don't see the other-handedness of each of those particles, the neutrinos and the antineutrinos. You would expect to see a right-handed neutrino. Now, what could be happening is that antineutrinos and neutrinos are in fact the same particle, and that a neutrino is the antiparticle of a neutrino itself. Now, this would make it a Majorana, named after an Italian physicist who proposed it, type particle, and not a Dirac particle. And this is one of the biggest unanswered questions in physics, really. But if it is a Majorana particle, then there might be these different varieties of neutrinos that were around at the beginning of the universe, in the Big Bang.
Wow. Okay.
These are heavy versions that basically decay down into the neutrinos that we see now. The lightweight ones, you get the heavy ones at the start of the universe. And looking at the maths of the standard model, what happens, you get this leptogenesis, which basically means that because of this asymmetry that we're seeing in antineutrinos and neutrinos, this will tie into this asymmetry between when leptogenesis happens, and you actually get this asymmetry between leptons and antileptons that then decay further into this baryonic matter that we see. And if you have this disparity between the two, you end up with more matter than antimatter. And of course, they've been looking and trying to solve this problem about whether neutrinos are Majorana or Dirac particles, but that's been incredibly difficult to achieve. And there's lots and lots of big and beautiful experiments trying to find this, but it relies on the half-life of beta decay, because if you have this double beta decay, which is basically where two neutrons turn into two protons, but if the neutrino is its own antiparticle, it can be used again to turn a neutron into a proton itself, and so you don't see any neutrinos coming out of that reaction, out of this double beta decay. And if that's the case, then yes, it is a Majorana particle. But yes, this beta decay could be taking a few trillion or a few thousand trillion years of half-life to actually see it. So you have to have enormous amounts of material and very sensitive equipment to try and capture this one event of double beta decay that would show either way whether the Majorana or Dirac particle neutrino.
Are you basically saying, Matt, it's bloody difficult to find?
That turns out that it's the opposite to this, CP violation, is that it's turning out to be incredibly difficult to find. So on one hand, they've had a lucky break, and on the other hand, it's been a lot harder than they thought it was going to be. So basically, we're one step closer to knowing, because we can see that this changing flavour is showing that we've got CP violation, almost certainly, but not certain enough at this leptonic level. But we need to know whether this thing is a Majorana type particle before we can say, yes, this is it. We have discovered it.
So let's hold on, please.
So yeah, Jamie, I want to just, because this Super Kamiokande observatory is so special, I just thought I'd just say how it worked.
Let's do it.
You can see the picture now.
It's stunning.
And yeah, you see the two little people in the boat.
Yeah. Wow.
It's just insane. Anyway, so yes, it's a massive underground lake. So you've got this massive stainless steel tank, 40 meters high and 40 meters in diameter, filled with 50,000 tons of ultra pure water. And lining the walls of this tank, and this is what makes it so beautiful, are 13,000 photomultiplier tubes. And they detect this thing called Cherenkov radiation. So when a neutrino interacts with electrons of nuclei of water, that's this ultra pure water, it can produce an electron or positron that moves faster than the speed of light in water. And although that's still lower than the speed of light in a vacuum, thank goodness, or else we'd be into new physics yet again, it creates the optical equivalent of a sonic boom. And that creates this cone of Cherenkov radiation light. And it's from that the sensor can detect the direction and flavour of the incoming neutrino.
That is so beautiful. I can't stop staring at that photo.
Yeah, no, it's insane. It's such a beautiful...
We will put that up on our Instagram accounts.
This could be a very, very important paper, and it certainly gives scientists the will to carry on down this road. Of course, it could still be a dead end.
Wow, what an incredible story.
Yeah, big time. Jamie, would you like to hear my conversation with Mr. Kelvin Long?
I've never wanted anything more.
Well, a cootie.
Roll it.
The Interplanetary Podcast, putting the ace Back into space!
So I am joined on the podcast by Kelvin Long, who's a fellow of the British Interplanetary Society, who represents the Interstellar Research Centre and has been involved with lots and lots of various different space-related institutions and others outside of that. A bit of a polymath. Welcome to the show, Kelvin. How are you?
I'm good, thanks. Yes, like everyone else on lockdown, so enjoying the sunshine there.
Yeah, so I'm assuming you're enjoying lockdown a little bit because you're a prolific writer and you like to get down to studying stuff.
Yeah, that's for sure. I work from home, so it's pretty helpful to have my office at home. However, I also have 2 small children, so they're very distracting, and I have to lock the door. But I'm managing to get a few papers written and trying to get some books progressed. So that's helpful.
Yeah, I think most people know you as a Interstellar guy. Who was your inspiration, and and why did you get into researching interstellar travel?
It's an interesting question. I mean, my own journey in space, interest in space, goes back to when I was 14. I went into a museum in the Potteries in Stoke-on-Trent and saw an Apollo exhibit. So that started my interest in space. Jumping to Interstellar, I think really happened from 2 angles. The first was when I was doing astrophysics masters at Queen Mary College. I met Martin Fogg, and he was a prolific author and pioneer of exoplanet sort of modeling and free floating planets and so forth, and wrote the very first book on terraforming of Mars. And he introduced me to the British Interplanetary Society. Of course, once I discovered the BIS, I then began to learn about Project Daedalus and meet Alan Bond and some of the others, Bob Parkinson, Jerry Webb from the Daedalus team. And that really got me to think about that whole field of interstellar and how different it was to interplanetary exploration. In particular, I was interested in doing some projects, but I was quite young at the time. So my first entrance was I'd done general relativity at university, would study black holes and cosmology. And so I started jumping into warp drive metrics because that was applications of GR, first appeared in the field in 1994, Miguel Cubier. And but after spending a couple of years on warp drive, realizing that it just breaks so many laws of physics and it's very difficult to try and build a warp drive, I got a bit more practical, and that's where the kind of genesis of the idea of Project Icarus came about. And what I observed was when I was looking at the interstellar community, there wasn't really a lot going on at the time. There was a couple of organizations that were sort of existing. The Tau Zero Foundation was the main one, run by Mark Millis, United States. He used to work for NASA, and but they weren't really doing much, and the BIS itself wasn't really doing much in interstellar studies. So, and a lot of the people that have pioneered the field had either passed away or moved on. Recently, we just lost Freeman Dyson, who was one of the other pioneers in the field, who I also knew. I really wanted to get some activity going in interstellar to really pick up the energy in the field, and then think about building a collective community that focuses on the stars. And this was serendipitous because, of course, at the time, we started to get the exoplanet discoveries. We started to find the first evidence of planets around other stars. Of course, now I forget what the number is, but we must be over 3,000. So once you have planets, then the question is, well, how can we get there? That's not to say that the only purpose of exploring space is to go to planets, but certainly that is an interesting factor. And my journey really started from that, and I've been involved with lots of different interstellar organizations since, either co-founding them, founding them, or helping other organizations. And it's been an up and down emotional journey, I must say, but it's been very interesting. And I feel a bit like Thor Heyerdahl on the raft when he's trying to cross the Pacific to get to the Pacific Islands, Polynesian Islands. And I feel like I didn't quite make the island. Like I crash landed somewhere, but I'm not quite where I want to be yet. And I look around me at what's going on in the field, and there's a lot of good work doing, but I still feel we're not quite going in the right direction to bring interstellar studies into the mainstream. And given that, the things we're thinking about at the moment, such as the pandemic, which has really gripped the world, I think that it's more important to have a long-term vision that goes beyond just what we're doing tomorrow or next year, or even in 100 years. Where do we want to be as a species in hundreds of years from now? And so I think Interstellar has a role to play in that.
Yeah, actually, I couldn't agree more. I was listening to Anne Druyan, who was Carl Sagan's wife, pretty much saying exactly that sentiment about we need to decide what we want to do in the future so that we can actually draw a map to get there. And obviously something like interstellar travel is such an interesting concept. It'd be really good to outline the real problems of interstellar travel, what, kind of the key points of why it's so difficult.
Yeah, that's a good question, actually. Unfortunately, I mean, I love science fiction. I've got an enormous science fiction collection. I should have mentioned, when you're talking about who influenced me, Arthur C. Clarke was one of the big influences on me. I read all of his books. And many of them featured star drives. So that got to be interesting in the technology. I think the problem with science fiction is it makes it look easy. It's a bit different with Clarke because he actually included some of the physics and engineering in his design, such as the Discovery 2 in 2001. But suddenly Star Trek, Gene Roddenberry, which, there's a beautiful book, The Making of Star Trek, where he describes his requirement for the starship, where he didn't want it to have any engines or anything like that, or fire coming out the back. So that's really created our perceptions of what going to the stars would be like, FTL travel. And so with Star Wars, those are the two big sort of poles in the tent in science fiction films, at least. And unfortunately, it's not quite like the sound barrier. I mean, the sound barrier, which was broken in 1947, 14th October by Chuck Yeager, that's a very different phenomenon. But I think people tend to think that the speed of light is just another barrier that can be broken. But there are fundamental reasons in physics why we can't go faster than the speed of light. However, there is an opening there because Einstein's physics tells us that actually space itself can go faster than the speed of light. It's called superluminal, and that's in fact what happened at the Big Bang expansion, superluminal expansion of space. And so, but when we actually get to the nuts and bolts of technology, like the Voyager probes, how difficult was it? With 1977, we sent those Voyager probes, and they were only at 130, 140 AU. The nearest stars are sort of 240, 50,000 AUs away, Proxima Centauri, Alpha Centauri stars. So in order to get there in, say, even a century, you would have to travel at something like 2,500 AU per year, and AU being the mean distance between the Earth and the Sun. The Voyager probes are traveling at something like 3.5 AU per year. So several orders of magnitude in scale. If the velocity is several orders of magnitude in scale, that implies also for the power systems, they have to be, instead of just multiple hundreds of watts, which is what something like the Voyager probes would use, which run out in 2025 because the power degrades, you need something else to power the system, maybe a much bigger nuclear reactor. And it also has other problems like communication problems, because now you're communicating over much longer distances. When you look at something like energetic reactions like Daedalus, designed by the Daedalus team, Alan Bond and so forth, this was using fusion fuel. And you actually look at the numbers that's required to push something like that to the stars, and it comes out something like 40 megawatts per kilogram, which is just phenomenal. And we're talking about terawatts, jet powers. These are the sort of metrics we use in propulsion terminology. And this is just when I give talks at NASA, for example, and I've spoken to all of the NASA laboratories, I always make sure I give these numbers because it's my way of saying to them, look, I know it's really hard. I'm not up here pretending that we can build a starship tomorrow. I know that when you run the numbers, it looks very problematic. And I never say impossible. I just say problematic. However, when you look at the advances that have happened in the last few decades, I think it's certainly the case. We can't no longer say it's impossible. Nobody can say that. And as you know, there's a project Starshot, which perhaps we'll get on to talk about later, which is an active project at the moment to actually send something out there. So I remain optimistic that over this century, and my personal goal has always been to work towards before 2100 launch date, is that we will be sending our first starships towards the nearest stars. But if we take that Polynesian model again, as Freeman Dyson used to refer to, there's other things in between. There's the rest of the planets in our solar system. as possibly brown dwarfs or other dwarf planets that are out there, free-floating planets which we can explore, the Oort cloud, the Kuiper belt. So these are precursor missions which we also need to be launching along the way.
Yeah, so in terms of the most promising near goal interstellar travel, would you say that is something like the Starshot type of propulsion?
Yeah, so Starshot, as you know, is a directed energy beaming method. We'll talk about specifics of the technology perhaps a bit later, but and it's currently costed to be of order, I think it's 10 billion, the last number I saw, to actually launch the first flight of a gram scale probe. So this thing is grams in mass. But actually, there's other projects underway. I've been involved for the last couple of years with John Hopkins Applied Physics Laboratory on a 1,000 AU mission. Originally, there was a proposal in the 1990s from JPL for a 1,000 AU mission, and that unfortunately didn't go anywhere. That was called TAU, 1,000 Astronomical Unit mission. But the Johns Hopkins people were trying to resurrect this idea. And certainly, I mean, the idea of, we used to talk about 200 AUs, but given that the Voyagers are effectively there philosophically, you know, they're at 140 AU-ish. So what's the scientific advantage to sending something to only 200 AU? Okay, so you're taking measurements of the same particle populations, charged particles, the plasma and helium sheath and so forth, which is very good because it helps you to understand your data a bit better. And we want to understand better the structure of the heliosphere bubble. But really, we want to know what's beyond that, what's outside that heliosphere bubble, what's in the Oort cloud. And 1,000 AU is just a good number to try and go for. And certainly technologically, if we wanted to send one, if let's say we had a program to launch one within a few years' time, and it was government funded or privately funded, and there was a decent budget of already billions to do it, we could certainly launch that. We know how to do it today. It's just really, it's not necessarily about the propulsion system, it's more about the payload, what you actually want to send. And this is one of the issues with Project Starshot, of course, because Project Starshot is so small in mass, gram scale. The question is, what sort of payload can you fit on that, because it's so tiny? And what's the value of the science you're doing? And therefore, does it justify the economics?
Well, yeah. Can you describe? Yeah, even though the propulsion isn't important, can you describe in a little bit more detail that 1,000 AU mission, what it actually looks like, or is that something that's not really pieced together? You've just got some numbers, or is there a specific look to it?
There's no design at the moment, but what there is they're basing it on the Pluto New Horizons idea as a reference. So it's something like a 30 watts. 30 kilograms mission. So it's something like a New Horizons, so maybe 500 kilograms in total mass that you would send out to 1,000 AU. So it would maybe do a flyby of one of the other, either one of the planets or one of the dwarf planets like Eris or Ceres, or there's speculation that there's an object that's much further out. There's Planet X. So could we do some astronomical observations of that? And suddenly, in terms of justifying it, we only have to look at the images we had of Pluto, even from the Hubble Space Telescope, which has been a fantastic achievement. And you compare that to the images that New Horizons has taken of Pluto. And they're just not comparable. I mean, and it really does justify why we need to send probes. I wrote a paper on this recently, published in JBIS, presented at the IAC in Bremen last year, I think it was, or the year before. And arguing that, there is an argument for why we should be sending probes and not just building big interferometers. But certainly 1,000 EU is a good target distance. And there's people been working on this idea for years. Ralph McNutt, Claudia Micconi have really been trying to push this mission. I would love to see European Space Agency or NASA collaborate together to get behind such a mission, because it is viable today.
Obviously, when you start talking in billions of dollars, and particularly when it gets to tens of billions of dollars, you're talking about, you have a choice between something like the James Webb Telescope and a 500 kilogram probe out to the outer solar system. So, how do you weigh up the science that's gained by each?
Well, I mean, in the United States, they have the decadal surveys, which is every 10 years they review what the science objectives are as national priorities. So that includes sort of galactic and planetary and heliospheric. Now currently, the Johns Hopkins study is a heliospheric decadal proposal. So its main focus is on the plasma sheath, understanding the solar heliosphere. But it's an interesting one because you can also do some planetary science along the way, which is you would end up having planetary sciences involved in that. So I do think it has to be driven by the science, but there's also an argument for getting out there and just seeing what's out there and making discoveries with things we didn't even know existed. I mean, building a space telescope like Hubble or James Webb, and I've been to Goddard and I saw James Webb telescope being tested when it was there in the huge satellite sort of clean room. Also, I was lucky enough to see the solar probe being thermally tested in the vacuum chamber at Goddard at the same time, which is really cool because myself and my family's names all on that probe, so that's good to see that. I think you do have to do, a comparison of the science benefits and then justify the costs. I don't think it's reasonable to just spend enormous amounts on something that doesn't give good science return. Having said that, Breakthrough Starshot, which is at the moment a completely privately financed initiative. There's 100 million at the moment been allocated, and Stephen Hawking was the sort of chief scientist on the board before he passed away for this project, and I'm on the advisory committee for Starshot. That's being led by Pete Worden, who's a former NASA Ames director, and also Yuri Milner, who's the sponsor. And that is privately financed, and it's, as I say, 100 million R&D money at the moment for the first sort of 6-7 years. And that's making really good progress. Lots of good papers coming out, lots of universities involved in doing experiments. And hopefully that will move forward towards a full-scale launch at some point, maybe a precursor probe, a test mission, maybe around the moon and back or something, using laser beam technology. Sometimes it takes private financing to do these things. I mean, just look at Elon Musk and SpaceX, what they're doing, which will have, with the reusable rockets, will have a revolutionary effect on the rest of the launch industry. Because what would it take to get the rest of the launch industry to look at those reusable rockets? So if he brings the cost down to, I don't know, $1,000 per kilogram or something eventually, which is also what SSTO was attempting to do with Skylon in Britain. This will have radical effects on the rest of the launch industry, which also means it's now cheaper to put telescopes in orbit. It's also cheaper to launch space probes. So it has an effect on the whole system. I know Alan Bond's view has always been that you have to break that bottleneck. You have to bring that launch cost down first, because mass scale exploration of space is not going to happen unless you can do that. Yeah,
I mean, Musk has been talking about $300 per kilogram for Starship, so that which is better than the space elevator. So that'd be pretty phenomenal. But
one thing we should say is that although the name is kind of called Starship, it's definitely not a starship.
No,
by any definition, it's not a starship. But who am I to question Elon Musk's naming rights? So.
No, but I suppose it may facilitate starships. I guess, but like you said, because it changes the paradigm, doesn't it, of actually getting things out of Earth's gravity well, which is one of the sort of big points. Now, while you were talking there, I was thinking about this. Just the propulsion of Starshot, where you've got a laser that's pushing something to relativistic speeds. There is a connection, isn't there, between interstellar flight and looking at it, because the energy is so massive. That's what's required. That you essentially will always build something that becomes extremely dangerous. And when I say extremely dangerous, as in it becomes a weapon of mass destruction. How do you ever get round that particular sort of problem? Because I can see with Starshot, when it actually comes to interstellar missions, you're going to need laser banks that can be obviously used for nefarious, lots of other ways you can use it, and it become dangerous.
Yeah, you're right. I mean, I think it was Heinlein, the science fiction author, who said something like any advanced propulsion system can be turned into a weapon. And it is true. I mean, even Daedalus, Alan Bond used to say, you could never look at the Daedalus engine because it's so luminous and so intense, it would just blind you. And never mind being in front of it. I mean, you couldn't launch it from Earth orbit, which is why they launched it from one of the moons of Saturn, theoretically. Starshot has the same problem. It's directed energy. Of course, the US has a long history with Star Wars program under President Reagan and so forth. And well, I mean, if you look at the original proposals for directed energy propulsion, which really came out of Robert Forward, who's a brilliant American physicist who unfortunately died, but he did such an amazing work. He was on a quest to find propellantless travel. So he was looking at antimatter to start with, because that is much more efficient compared to, say, fusion. But then he started to look at sails, and then he started to look at lasers, and then also microwave beams, masers. And he really pushed the field. He even presented a paper, I think in 1976, to the US Congress, saying that we could build a program. And they said, when could we launch the first mission to the stars using this project? And he said around year 2000. So he was very optimistic. And this was something like a 1-ton probe called Star Wisp. But his architecture was based in Earth orbit. So it was using these massive Fresnel lenses to reconverge the beam, because the beams will tend to diverge, something called Raleigh's law. And so you have to recollimate the beam, because once the beam starts to diverge, you no longer have full pressure on your surface. So he would build these massive Fresnel lenses, like 500,000 tons in orbit. So that's an enormous scale project. Then you have a laser which gets light from the sun, pushes this sail, reconverges this beam, and then pushes on a 1-ton sail that's maybe, I forget the dimensions of it, maybe 10 kilometers across or something, and it pushes it to the stars. But in principle, I mean, if you look at the Gerald and Hill studies in the 1970s as well, they were talking about getting solar power from the sun. So similarly, you could use that same architecture to power the national grid or to push satellites. But you're right, you could also turn it on an enemy country and take out an enemy country. So I think the complications with these issues is one of the reasons that Project Starshot controversially decided to not go for space-based launch. So their architecture is to have ground-based beaming. So you'd have an enormous array of beamers on the ground, generating stuff like 100, 200 gigawatts of power, beamed up to a spacecraft in orbit, which has a sail which is only about 3 meters across, carrying a gram-scale payload. And in theory, you could shoot people's satellites down, but it would be difficult to, fire that laser at a country because it's on the ground. So that's one of the reasons I believe they chose to do that. They've also gone out of their way to make Project Starshot international, because they believe that there needs to be understandings and conventions in place and protocols. When you would fire this thing, you'd have equivalent of launch windows, just like rockets, they have launch windows. And those launch windows would be determined by whose satellite is in orbit right now above us, because you can't fire it if there's a satellite that's about to come over the horizon. So, and of course, with space getting very cluttered, that becomes more problematic, which means your window is probably going to get shorter. But, in the architecture, these things only fire for a very short time. You're talking about 5-10 minutes firing time. And they accelerate the probe to something like 10,000 G at 20% of the speed of light at 60,000 kilometers per second. So if you can find a 5 to 10 minute launch window, you could fire this thing. There's also the risk of people attacking the architecture on the ground and trying to misuse it, terrorists, for example. So there's a whole bunch of security issues around this technology. And so it does probably require, in the same way that a project like CERN was international, or the International Space Station, by definition, is international, something like Breakthrough Starshot will probably be an international project. It may be that there are primary partners involved, such as the United States, which is primarily leading the project. But I don't see any reason why you wouldn't invite other countries in to be involved with it. and for them also to fire their own experiments, their own probes with their own technology. And that is really exciting because now you allow for innovation in the probes themselves. One of the things that justifies Project Starshot is continued miniaturization of electronics. And, we're talking about launching this thing in maybe 20 years' time. And if microelectronics continues to follow Moore's law, then who knows what we can fit in such a tiny package.
Yeah, well, there's plenty of room, isn't there, down there, as Feynman said. So just to give people a kind of feel for how hard it is to get to another star, if you were to use conventional rockets, like if you were to use the space shuttle going flat out with chemical rockets, and it had to get to Proxima Centauri with just in a human lifetime, say 80 years, it had to get there. Conventional rockets, it would need a fuel tank the size of the observable universe. And I always think that says everything. Just the amount of energy that's required to push you in a reasonable time frame, such unbelievably vast distances. It's just the vastness, isn't it, that's just mind-blowing and almost incomprehensible compared to even the size of the solar system, which in itself is incomprehensible. So with something like Starshot, when you send a small gram probe to try and to get there with this enormous amount of energy, the first things that pop into my head is, how does the probe itself survive 10 minutes of this intense energy? And how does it survive the journey? Because it's not just empty space, is it? It's got to traverse space that's bound to have, I mean, anything of any size is going to rip that thing to tiny pieces. So how do you get around that?
Yeah, so just a quick comment on your other comment, first of all. The problem with chemical technologies, of course, is it's fundamentally limited to about 500 meters per second exhaust velocity, which is a fundamental restriction on its performance. Yes, so unfortunately, I've done a lot of work on particle bombardment. When I joined Project Starshot, my capacity is actually to be a member of the advisory team, which basically means don't do any work, just advise us and come to meetings, which is really fun. Great fun meetings, really good discussions, and we discuss all the sort of proposals that are being made and how we can move the project forward and so forth. But as a physicist, my nature is to do calculations. So I jumped into the particle bombardment issue because when the project was launched, Yuri Milner announced 19 sort of technical engineering and physics problems we needed to solve. And one of them is, as this thing's flying through space, what's the erosion of it? And that erosion is really down to two factors. The first is dust itself. There's an enormous amount of dust out there. And the second is to charged particles. So the hydrogen, helium, electrons, whatever else is out there. And so they all act to erode the structure. And they also potentially can be, they can charge the structure and cause flip switching, as we know from conventional space missions. Instances have actually happened. If an electron gets inside of a microelectronic circuit, it can flip switch it. So maybe you'd end up with an engine firing before you intended that to happen. So, but what I found is that actually the biggest effect is the dust. There are particles out there we believe as big as 50 nanograms in mass, which is pretty big. And these things are microns across in size. But when they hit your spacecraft, which is moving at 20% the speed of light, this potentially can have a devastating impact. It's like a little miniature bomb going off. But what you can do is you can look at the particle distributions, because there's an average massive particle, dust particles, or mean, and there's the smallest and there's the largest. And what you find, of course, is that there's less of the largest and more of the smallest, and there's a mean between them. And so you can play a statistics game. And I think what you do is, it's not the fact that you just launch one of these things. You can launch many of them, because once the architecture is in place, you can just launch thousands of these in principle. And then the probability of you getting through is quite high. So you have to accept that a certain fraction of them will be lost because they will be hit by a large dust particle. But a certain fraction of them will get through. What that fraction is, I don't yet know, because it really depends on our knowledge of the interstellar medium is pretty good, but there's still a lot we don't know about it. We've got an idea of what its matter density is, what the proportion of particles to dust is, and so forth. But this is one of the reasons why we need the 1000 AU mission and the post Voyagers, because we could really, start to take some better measurements. One of my concerns about the Voyager probes, very successful, but I learned that, for example, the magnetic field measurements, the actual magnetometers on board were designed to measure magnetic fields around Jupiter, the gas giant Jupiter, and those magnetic fields are quite large. And so the sensitivity of the instruments were designed to measure large B fields. But of course, when we're talking about B fields in the interstellar medium, they're much smaller. And what I discovered is that the actual, what's called the standard distribution, if you like, the margin of error on those measurements is what's called 1 sigma, which is very low. In other words, we have the magnetic field measurements from the interstellar medium, but we have low confidence that those are giving us an accurate picture. And so we need to send another probe or more probes to actually characterize that data a lot better, so that when we come to launch in Starshot, we know exactly what we're flying through.
Are there any numbers when it comes, because I'm thinking if you're launching thousands of these probes, how expensive is the actual launch of a probe in terms of switching on the laser beam and working it for 10 minutes? What's the cost of that compared to the cost of building this tiny little probe? Presumably it's the laser that's more expensive than the probe at this point.
The actual cost of the probe is tiny. It's the biggest cost by far is the laser. The problem, if you look at the moment, so we talked about Moore's law in electronics, and we know roughly where we need to be in 20 years' time with that technology to get more instrumentation on board the tiny little probes. So these things could, in principle, could be as small as a grain of sand with a 3-meter sail pushing them. So at the moment, the cost of lasers is something like $100 per watt. Forgive me for using dollars, but
yeah, that's fine.
It's of order, so you can use pounds and dollars. So what we need to do to bring the cost of the flight down to about $10 billion is we need the cost of the laser to come down to about 5 cents per watt. So you can see that's an enormous reduction in cost, but that's over the next 20 years. And the guy that's really pioneered a lot of the studies on this and was one of the founders of Project Starshot is Phil Lubin from University College Santa Barbara, California, Santa Barbara. And he's done some extrapolation studies, and he believes that the cost of lasers will come down to that sort of level over the next 2 decades. And that then makes the mission viable. If we can't, then the total cost of the flight, in terms of building the architecture at least, just to get one flight, it then goes up. And so it's difficult to justify it. So you are dependent upon that. There's 3 kind of holes in the tent for Project Starshot. One is the miniaturization of electronics. The other is the laser, getting the cost down and being able to. No one's ever built a gigawatt power laser. That's the other thing. Got to build gigawatt power lasers. And thirdly, it's the array itself. Because remember, we're not just talking about one laser. We're talking about potentially hundreds of these lasers, all converging at a point. This is called a phase laser array. And it would work in a similar way to, say, fiber electronics, fiber communications technology. So to converge that light signal onto the spacecraft. One of the other issues you mentioned was the possibility of ablating the spacecraft, the sail itself. Greg Matloff, who's one of the members of the advisory committee, has done a lot of good work on the possibility of using graphene technology. And there is, some belief that if you make a sail, if you think about solar cells from the sun, they require high reflectivity. So all the light that's hitting it wants to basically be bounced back off. That way you get 2 times the push. That's the momentum that pushes the sail forward. Well, with these graphene cells, potentially you can reflect a lot of that energy. So there's a lot of work being done in graphene cell technology, and that would allow you to absorb the high temperatures as well, which may be 1,000 Kelvin from these lasers, so that you don't completely irradiate it.
The other thing, of course, is you've got these tiny little interstellar probes now that are whizzing their way across interstellar space. But once they get to their targets, there's no slowing down, is there? They're just going to whiz past the targets, and you've got a very small window of opportunity to do science. So what are the problems around that particular part of this?
Yeah, you're right. It is a flyby mission only. We had the same problem in Project Icarus, building on Project Daedalus. Project Daedalus was also flyby only. It flew through Barnard Star in principle in 4 days, and this is a massive structure. We decided when we started Project Icarus, which is fusion successor to Daedalus, that we would decelerate. We've demonstrated on paper we can decelerate into full orbital insertion. I think our argument is that in order to justify the cost of such a mission, you have to be able to put orbiting satellites in place, observers. You have to put atmospheric penetrators in and ground landers. Because then you can visit all of the planets in that system, and you can get so much science. You can look for evidence of microbes or whatever, look at the geology in much more detail, get through the cloud layers. A flyby probe is so limited, but Starshot, it'd be very difficult to try and decelerate these probes. There has been work done on looking at the deceleration. There was a paper, I think only a couple of years ago, talking about the possibility of decelerating them in the atmosphere of a planet, but I'm not sure that works. The fundamental problem is these things are moving at 60,000 kilometers per second. They have enormous amounts of energy. You just do the half mv squared calculation, you see these are like little bombs coming in. In terms of stars, for example, if you wanted to do gravity assist around a star, your spacecraft needs to be going at a comparable velocity to the star in order to benefit. So you probably want to be going something like 500 kilometers per second or less in order to get any benefit from a gravity assist. So gravity assist is ruled out. So really, these are flyby probes. But the current architecture was that we just want to take a photograph of an exoplanet close up. I mentioned the difference between Hubble and New Horizons in terms of what we got for Pluto. So that argument is certainly sound in terms of if you just take one photograph of an exoplanet, you should get a much better image, provided you can get the data back, than you would from long baselines, interferometers in Earth orbit. But there is a cost issue. But taxpayers are not funding this at the moment. This is a privately financed initiative funded by Silicon Valley billionaires mainly. And I guess they can choose to spend their money how they want to, and thank God they are. But I can see a point in the future where government might get involved in helping to fund some of these projects if they start to show a significant science benefit.
Yeah, I always struggle to think of, because you're right with the electronics side of things getting smaller and smaller and smaller, and I don't doubt that in 20 years' time we'll have electronics that are capable of doing some of the electrical side of things, but the things that I do find hard to wrap my head around is with things like you say, just taking a photograph of a star as you whiz past, or a planetary system as you whiz past. It is the actual camera itself. It seems that kind of technology isn't really that shrinkable when it's all about resolution. There is there's very specific mathematical equations about the resolution that you can get with aperture and things like that. How does that work? What's the work that's done on that?
I'll have to pass on that because I'm not an optics person, camera person. I know that when I was in Initiative for Interstellar Studies, which I co-founded with Rob Swinney, we did a project called Andromeda project, which is actually how I got involved in Project Starshot. And we did that study for Project Starshot before they went live. And they basically said to me, I had a meeting with Pete Warden in San Francisco, and he said, okay, so we're launching this project. We're looking at launching this project. 10% of the speed of light is what he told me at the time. I didn't know later it was going to be 20%. Something that's gram scale in mass. Go away and see what you can design. So me and my team, in 3 days, we produced a report. And bearing in mind, I was flying from San Francisco back to, I got stranded in New York for the night, and then back to England. On the plane, I was calculating, pen and pencil and calculator out. And my team was all calculating. We had about 15 people involved in it. And by the Tuesday morning, we had a paper on their desk. And we managed to get the whole mass. I think it was 420 grams was our probe mast, moving at 10% speed of light, pushed by a 1 gigawatt laser in Earth orbit. Okay, and what we did is we had a segmented lens array. So instead of having one collimating lens, we had 10 of them going out to Mars, about 2 AU, and that was to recollimate the beam. And that was using architecture created by Jeff Landis, who's a NASA Glenn scientist. And we demonstrated that was possible in principle. But what we did is we stuck quite a big camera on it. Our systems were kind of wafer size, like a stamp size, so 420 grams. But their initial response was, "You're too mass heavy." We went away, stripped, because we had lots of instrumentation on it as well, because we were driven by the science. We stripped off a lot of the science. We managed to get the whole thing down to about 25 grams or so, or 28 grams. So I don't know. I mean, what cameras can do in the future. I don't know. You're right. I mean, because it's all about collecting photons, right, on the surface. So if you have a smaller aperture, presumably you're collecting less photons per surface area. So I don't know. I mean, maybe there's things you can do where you have several of these and they're kind of linking up together, and you're combining the images. I would say that's not got a lot of attention because it's considered a low priority, because it's really just a microelectronics issue, but an optical issue as well. And I'm not qualified to speak on the shrinking of telescopes to that size.
Yeah.
But our focus has been on the big poles in the tent, which is can we build a laser that big? Are we going to vaporize the cell? Can we survive the journey? And once we've ticked all those boxes and we think we can do those things in principle, then it's like, okay, what's the probe going to do when it gets there? Can we take the images? Can we get the signal back? And that's another issue.
I was going to say that was the big one I was going to ask next. Is in terms of, because you're now at an interstellar distance, getting a signal back, you'll need quite a lot of energy to do that. So with something gram sized, it's quite hard to perceive of where that energy comes from.
Yeah, so we've had a lot of interesting discussions about that, and because when I give talks on Project Starshot, it's invariably the question I get the most is how are you going to get the information back? And I'm not a comms guy. I can just about do a link budget calculation. I'm a propulsion guy mainly. But the guys at Breakthrough are confident they can do it. I mean, we got David Messerschmidt involved, who's one of the world authorities on interstellar communications, and he's written several massive papers on it, and they believe they can do it. I mean, you're talking about the power of this signal is something like 20 watts, which is incredibly small power. But so maybe you've got to try and pick that up over light years distance. But what they are planning to do, you won't be using the Deep Space Network probably. What you would be using is the laser beam itself. So the laser beam, it basically doubles as a receiver. So you've got this huge ground space station of these lasers on Earth, maybe in a desert somewhere, and there's hundreds of them. And together they could also, in principle, pick up that signal collectively. So that's the current thinking, is that they would double as a receiver. There may be other ideas, like you could put a receiver on the quiet surface of the moon, maybe on the backside, and try and pick a signal up for it where it's quiet. But or you could if you had a probe out at 1,000 AU, maybe that could play a role in bootstrapping that signal to boost it up to a larger amplitude. It's not something, the communications is not something that the guys have focused on with too much priority early on. As I say, the focus was on the SAL and the laser, because the SAL, which is another issue in terms of stability of the SAL. But I think that emphasis has now changed, and they now have formed a communications subcommittee discussing it. But from the initial discussions over the last 2 years, they seem confident that they can pick up that signal, which is amazing. I'm just not privy to all the details of the specs.
While you were sitting there, I was having the idea, based on something I was talking about on the podcast a couple of weeks ago, is as it's going so fast past the star, it will get to the point where it's at the gravitational focal point of that star, which of course you could then use to transmit the signal and have it amplified by the star itself back to where we are. But I guess
yes, and that's at about 1,000 AU, by the way.
Yeah, yeah. So yeah, that would be, I guess, one way of doing it. But yeah, I mean, I'm sitting here. My gut feeling is that if we want to do interstellar missions, that we need big craft to do it. That there's going to be, at the end of the day, I think that it's going to have to carry its own propulsion, be big, so that you've got this enormous power for doing things like sending signals back, or doing inserting yourself in orbit, or going on to do other missions, etc., etc. Where does that then take us? Is that something that's been looked at? Sort of the actual vehicle itself being having the propulsion on board and the technology and all the science, etc., on board.
Yes, it is. I mean, you're right. I mean, the projects like Starshot and other ventures we might launch are really exploration missions. They're certainly not colonization missions. They're just really taking the temperature of the water, if you like. They're telling us a little bit about what's out there, improving our knowledge of the interstellar medium or the properties, confirming that, yeah, we think there's an exoplanet and now we've got a picture of it. This will help start building. It's reconnaissance, right? So ultimately, humankind has to build a starship and get out there. It probably wouldn't be like Enterprise, with a big warp drive, but it may be similar in that you would have literally crew members with families on board. I mean, let's assume that we don't achieve any life extension, as some people are working on at the moment, and we only live to sort of 80, 100 if we're lucky. Then the first crew that's on board, maybe they're in their 40s, 30s or 40s. There's an argument you might want to go younger. But certainly, to get to the stars in sort of even 100 years, as I say, you have to go incredibly fast, 2,500 AU per year. And but even when you get there, your crew has died. And so now you've got a new generation. So you have to have a generation of babies born on board. And then you have to train them to run the ship, to prepare the power systems, to, repair the communications, and to do the astronomy and explain to them why we're out here, And what I find really interesting is that, it's when we look at history, all the great adventures of history, whether it's Columbus who discovered America, he didn't discover it, of course. There was lots of people living in America when he got there. But all of the great, mentioned Kon-Tiki and Fort Heyerdahl, that sort of mission. All the great adventures of history. When you think about all the adventures we still have to have, whether it's, in the past climbing Everest, in the future we're going to climb Olympus Mons on Mars. This is a great adventure that still awaits us. And without doubt, it probably will be full of tragedy. People will die because some missions won't be successful, and some will be successful. What I find interesting, actually, the idea of a world ship, which is what we're talking about. And again, Alan Bond and Tony Martin produced some of the first pioneering papers on this. They looked mainly at the propulsion and the habitat mass, how much atmosphere you need, and so forth. But what I find really interesting is whenever I get into discussions of world ships, it's not the technology that dominates the discussions, it's the social culture issues. It's like, what kind of a governance structure would you have that works? Because can we say with confidence that we've tested all of the governance structures on Earth at the moment, all our different ideologies, that we know which one works? Because so far they've all got their downfalls, and we look at how we're handling the COVID-19 situation. It's doesn't necessarily reflect well on our governance models. So how would you manage a starship of maybe 1,000 people? How would you police it? What would happen if there was a pandemic that broke out on a starship? Right? You're going to isolate everyone inside their tiny little crew cabins. How much support mass do you need? This is why the studies by Gerald O'Neill in 1970 is very important, because I think he concluded you need something like 65 tons per person of supporting mass in terms of water, food, oxygen, for a space habitat like an O'Neill colony. The Russians have done studies. They conclude, typical of the Russians, you could get away with a lot less, like 15 tons per kilogram. But it's something in that range that, maybe sort of 10 to 100 tons per kilogram for a human being. And so if you had 1,000 people and that just run that numbers up and you start to get a massive structure, never mind adding on the propulsion system, the power supply. So probably what you'd want to do is to have a strategy where you'd have either several starships or is one starship, but you cordon off. So there's different colonies, right? So and those ideas have been explored in science fiction. This way, if there's any problem in one, the others can help, or you're isolated from the problem. If it was a pandemic, for example. And you need to have the ability to automate reusable materials on board. So if something breaks down, you need to be able to manufacture those materials on board. And this is the beauty of 3D printing, because it has massive implications for the future of space travel. Ultimately, when I've looked at all these ideas for world ships, and they're very romantic, and I quite like them. One of the I think thoughts I've had is that this is probably not the way in the long term we're going to explore deep space. And there's a limit to how far you can go, which we can get to. I think it's more likely that maybe you'd send something like a Starshot probe, which would be easier and cheaper to do. And as it gets towards that stellar system, it grows itself, right? So it's like a biological, organic starship. So it's starting to get the light from the stars. It's approaching it. And so it's got energy. And that energy starts to grow the structure in the way that a plant would grow or a crystal would grow. And it starts to construct its own starship. And maybe once you've built the fundamental structure, it then, the program would tell it to start to then take the embryos that you've got on board and to start to grow those. So maybe you start to grow a few crew members. And the robots, the artificial intelligence, which is what the program would be constituted on, will do all of this. They do all of this thinking. And then you get there and you arrive at your planet, or you arrive at your moon, or wherever you're going, or just your orbit, and you grow everything in situ. In principle, you can grow an entire civilization just from starting from that little premise. And I think that's probably likely the way deep space exploration is likely to go in terms of humans getting out there, unless we can find a loophole like wormholes or warp drive. And at the moment, the evidence is not strong that we could do that.
Yeah, I mean, it'd be a really strange. I mean, that's a great concept. I'm just trying to unpick all the very strange, odd things that can come out of the. If you send identical probes off to different systems and they've got identical crew members on board, and they can communicate to each other and go, "God, you look just like me." Yeah, there's a reason for that. Yeah, that's a very, very interesting concept. Not one that I've read in science fiction at the moment, I don't think. Is there any
another thought about that is that talks with governance models and so forth. If you were sending a whole crew of people, people can criticize certain ideologies on planet Earth, like certain religious belief systems. But actually, there is an argument that it may be that you need either a military or a strong religious kind of framework as the basis of that social culture in order to hold it together. Otherwise, you're just going to have people, having a revolution on board. The other thing I wanted to mention was I mentioned Arthur C. Clarke earlier. Arthur C. Clarke was a huge believer in the future, artificial intelligence will come. He actually described it as Homo electronicus. And he talked about this in Profiles of the Future, which I think was published in 1968. And he said that in the future, it's not that human beings will be driving the submarines and driving the spaceships. We will become them. Right? So we'll enter symbiosis with them. And eventually there'll be no distinction between us. So, we can actually experience what it's like to be an aeroplane or to be a submarine or to be a spacecraft. And so when we think about our artificial intelligence that gets to the nearest stars, that actually may be us. But then it goes to the question of what is us, right? So what does it mean to be a human? Is it our physical makeup? Because in principle, as you know, all of the senses right now, I'm speaking to you, and I have all of my senses, my sight, my hearing, my touch, and it's all coming through, but that's transmitting information to my brain, and my brain is creating some imaginary reality based on those projections. But if I could put my brain in a jar, and I could also get those same stimuli through those sensors, would I know the difference? Okay, so, and then we get to virtual reality, where virtual reality is going. So there's so much that's potentially in the future that it's really difficult to tell what direction it's going to go.
Do you have a roadmap for how you see interstellar travel? So we're starting off with presumably you think we're going to be starting off with Starshot style probes. Where does it go on to next? Where does it go on to next? And how do you see the roadmap of interstellar unfurl?
Yeah, I do. In fact, I just published an example roadmap in JBIS just in the last issue. Although I wrote that in 2011 for the 100-year Starshot. Yeah, I mean, whether Starshot ever gets to a launch remains to be seen, because there's lots of things that could, upset that program. But it's still doing fantastic research and so forth. You're right, there is an enormous gap between that and, say, world ships, big colony ships of people, which is, first of all, is the Voyager-like probes, which are much bigger in mass but doing more science, and then you go up to the next level. We have looked at those in Project Icarus. I should mention Project Icarus is the what we did is I realized that I wanted to redesign Daedalus, and so we set about doing that. At some point, we ended up with over 100 people involved. We've now got about 5 Starship designs, all of which are solving some of the issues of the Daedalus project, because there's lots of reasons why Daedalus wouldn't work. I think I heard Alan Bond say it had a 40% reliability of actually getting to its destination, because there's lots of things that break down. There's little bombs going off 250 times a second. I mean, the heat and the fatigue on that structure is just so. So what you tend to do when you look at interstellar roadmaps is, first of all, there's the distance. Where what's the destinations we can go to? So I mentioned Kuiper Belt, the Oort cloud. There's getting to the nearest stars, and there's whatever else is in between, which we don't quite know yet. Maybe there's more dwarf planets like Sedna out there, and then it's how can we get there? What's the technology to get there? So the propulsion system is one of those elements, and so fusion obviously is not quite ready yet. We've got a inertial fusion program on Earth. That's my background, is inertial confinement fusion, and there's mostly the magnetic fusion is making inroads, I would say. But there's lots of other ideas for fusion. There's antimatter potentially, if we could figure out how to keep it stable and bring enough of the stuff together. But then there's these light beaming ideas, solar cells, which are really, in principle, dead easy, right? Because they're just a huge reflective sheet with a large area collecting photons from the sun, which is pushing it. The problem is, as you know, as gravity falls off inversely squared resistance, so does light. And so as you get further away from the sun, the pressure on the cell falls off. So in my opinion, solar cells are not really a good idea for interstellar missions, unless you furl an enormous cell, like tens of miles across, really close to the sun. Then you can get the acceleration. But whether the material could survive that enormous luminosity, 10 to the 24 watts, whatever it is, from the sun, 26 watts. So that's why you go to directed energy, because you can beam energy, or you could beam particles. So there's lots of these propulsion systems. What I would say is that there's very little going on in terms of other possibilities. There's lots of conjecture out there about space drives, which is the idea of, there's the interstellar ramjet, the idea of mining interstellar hydrogen in the interstellar medium is sort of like a space drive, but it's not actually mining the properties of space itself, but it's mining hydrogen in space. But there's other ideas where actually we believe there may be energy trapped up in the quantum vacuum itself. And so if we could tap that, that would certainly enable a game changer. And there's very little research going on. There's been a few papers, there's been a few studies, and these programs just are not being funded with any kind of rigor and determination. So I would like to see some of that done. So if I was to sit down and someone said, okay, we're going to allocate several $1 trillion, which is what in the current environment, it's very unlikely because we just spent it trying to deal with the pandemic. It does amaze me how, by the way, when we had the financial crash years ago, we were suddenly able to produce billions of dollars to bail out the banks. And right now, I'm not saying we shouldn't, but we're producing, trillions to sort of help out with the economy and so forth before it crashes. And yet, when we get back to normal times, even Apollo was like 4.6% of its GDP. The actual spending on space is incredibly low. And yet, it's been estimated that I saw a paper recently that the actual return on investment for Apollo was something like $200 billion on the economy. So you get enormous returns in space. In order to build a roadmap, I would say we need to do more research first. It's not to say that I don't want to do those one-shot missions. I'm a big fan of the moonshot idea. The idea of it's not necessarily a sustainable program, but you just want to launch something, and even if you just do it once, just to see what you can find out and what you can do. Okay, so and that's what I think is the value of Starshot, unless it builds that architecture up and it starts launching thousands of these things, and then that value is amplified even more. But I personally want to see a lot more R&D done. I want to see the universities get more involved in interstellar flight, rather than it being seen as just a science fiction field, which I think historically it was. It's taken a long time to improve the credibility of the field. I mentioned warp drive. It wasn't until 1994 when a Cardiff University Mexican physicist, Miguel Cuvier, decided as part of his postdoc work to write a paper, because he can get away with it then, because it was just a Gedanken experiment, a thought experiment. And he wrote a paper on whether you could use general relativity, to actually give you something like the warp into space. And that produced thousands of papers that followed. It started a whole field of warp drive, when we would actually do it. And, in principle, we can. It's just there's lots of other things that, just like the thickness of the bubble has to be Planck scale in length. And it just creates such extreme energy densities that you effectively get like black hole singularities surrounding the vehicle. And it's just, there's loads of physics issues. So I would personally like to see more of the universities and even private industry get involved with some of these technologies. Maybe that needs to be done in a way that there's a contemporaneous benefit to human society. So for example, if you're developing more better power reactors than say the Voyager's got, or we can use at the moment, maybe those power reactors should also have potential to be used on Earth, right? So maybe there's an argument for that there's a parallel benefit to any technologies we develop. So that while you're developing the technologies for space, you're also developing the technologies to help Earth point one. And so there is a roadmap that you can go along, but I would say that at the moment we need to do more R&D, and I would say we need to spend at least a decade of rigorous R&D, or well-funded R&D with different institutions on all of the options. One of the bees in my bonnet is that if you look at all of the different studies for propulsion systems, for example, whether it's masers, lasers, fusion, antimatter, different types of fusion, cells, what you see is that there's no apples and apples comparisons. So when someone says, oh, this technology is better than that one, it's like, yes, but your payload was 1,000 times bigger and your mission time is this difference. And so what we need to do is we need to put things on a like-for-like comparison in order to see what the real potential is. And the best way to do that, I believe, is to throw those technologies, plug them into a mission platform. So like, let's say we decide we're going to do a 1,000 AU mission. So what's the different technologies that we can use and how do they compare, carrying the same payload, and do the same for an interstellar mission? And that's not really been done, in my view.
The Interplanetary podcast, putting the ace back into space.
There you go, Jamie. Super long little interview there.
I absolutely loved it. I can't wait for part 2. What a legend.
Yes, I will have more conversations with Kelvin. He's a very interesting character. We got into the philosophy of science as well, so it's very worth it. His Conscious Stars thing all started. He gave me a phone call, very, very kindly asked me to check his calculation about stellar parallax, which I did, and I got the same answer. I got the same answer as him, so I was very pleased with myself. So maybe I can call myself a scientist.
I think you should.
So, Jamie.
Yes.
What should people do if they want to support the podcast and conversely support this week your little charity? Next week, I want to nominate Médecins Sans Frontières.
Yes, that's excellent
because
choice as well.
that was offered by the patrons on the Discord channel.
Yeah, just a reminder, I am trustee of a wonderful mental health charity called Smart. And that's where your money will be going to. If you hop on over to www.interplanetary.org.uk, and there is information there on how to become a patron, and that's where your money will go. We're putting our money into the charity. Your money still goes to the podcast. So, yes, thank you very much. It's very heartwarming seeing all of these donations.
I want to wish all our listeners good health.
Good health.
In these crazy times. Do you know what's annoying, Jamie? I've been so busy at work.
Because
obviously
we're
having to change our style of teaching and all that kind of caper. That I just haven't stopped. But yes, I really wanted to do more sort of live shows and stuff like that. I haven't even been able to see all the other live shows that all our friends
well, listen,
have been
it's
doing.
going to happen. It's going to happen. We've just got to get through this last little bit, and then we'll all be let free again, and we can do fun stuff. So hold on, stay inside, stay healthy. Cheers.
Cheers. Bye-bye, Spot Cats.
See you soon, bye.
Bye-bye.